Good day, my name is Evgeny Cherkashin and I will present my talk entitled Technologies for Semantic Web as an Environment for Application Development and Integration. I present a group of authors from Matrosov Institute for System Dynamics and Control Theory of Siberian branch of Russian Academy of Science. The research and development of this project is as follows. The main objective of the activity is to construct data integration tools based on standardized semantic web technologies which were developed since 2001. We will in general consider the following list of topics. The first is application data representation, ontological model representation, document publication, some application integration techniques, and the model transformation techniques, which allows us to integrate in our development different model presentation of different aspects of application. Participating in various conferences, I paid attention to the technique of ontological models usage. This usage was based mostly on developing local or personal ontologies which are precisely described the domain. But since 2001, more than 20 years passed, and various research groups have already developed useful ontologies which describe existing domains in general. This description is based on standardized representation of these conceptual models using graphs. In their turn consist of triplets of this form: subject, predicate, object. This triplet graphically presented in this part of the slide. This is subject and this is object. These two nodes are nouns. Predicate is denoted as arrow connecting subject and object. There are also basic definition of the standard representation, which is based on notion of URI, Universal Resource Identifier, or International Resource Identifier. Here is an example of such an URI defining namespace, doubling, or literals. Literals are just the values having type string or integer. And hierarchical representation of the data about domain, and the basis of this representation is XML language, and all XML standard statements are also applicable to ontologies. A domain description finally represents a graph having two types of nodes. One subgraph denotes so-called terminological box and contains abstract notions and basic relations between them. And the rest of subgraph is so-called A box. It's a list of notions being instances. These instances can be, for example, records from the database. As we can see, the basis of the data representation is networked, so this representation has natural constraints. Each relationship can express just two argument relation, and if we want to express something more complex, for example relation with 5 or 7 arguments, we should use blank nodes, and this node is for joining various properties in one big relation. The difference between URI, which is used to point resources, blank nodes are also resources, but they have no exact URI pointing to them. There is various data representation formats for storing data about domain. The first one was resource description framework, which is strongly dependent on XML specification. These three formats are almost the same, and triples, turtle and notation 3, which represent triples as just a list of triples. For turtle and n3, there is a way of joining common properties related to one subject into local lists for more easier reading. And the last format which is useful for web application development is JSON LD. It is a kind of JSON format, and most of nowadays libraries support this format. The domain models are stored in files, documents, and mostly as resources on servers. We try to use the following software, which allows us to organize storage: OpenLink Virtuosa, use it to drive DBpedia; Apache Jena, it's a Java library for application development in Java; GraphDB, it is commercial. It has very good user interface for organizing storages and testing SPARQL queries. I personally use Cleopatra. It is implemented in Prolog language. It allows us to organize various inferences on the server side. Data can be loaded from files and documents, and also queried from the resources by means of SPARQL. Query language is useful to query triples and graphs. This is an example of such SPARQL query, and I should mention that all SPARQL services support federated queries. That means some subquery can be run on another server. In our last application, we used DBpedia to get Russian labels for notions. I forgot to say that word vocabularies denotes ontologies and used in scientific papers more frequently. So, standard vocabularies form cross-application platform. This relation RDFS label with literal GTURL is used to construct this figure of different relation between classes and subclasses of properties and names of the nodes taken from this RDFS label relation. And in general, this slide shows the resource cpec GTURL, existing relations between this URL as subject to other objects and literals. And in the last decade, there appeared new projects, sometimes called as Web 3.0, which is characterized with special technological basis oriented to web standardized data format storage and processing, open principles of data publishing, services for data storage and access. In general, it means that there is a special services which understand standardized vocabularies and provide a corresponding service for data storage. For example, there are servers that represent user data and authentication of this user for other applications. The second direction of development is forming so-called knowledge graph technologies. I spoke about semantic web, and the first, the notion of data and knowledge are converged into the something which is known. This knowledge form knowledge graph. Knowledge graph, as it is a kind of semantic web technology, contain data, relations, and metadata. Technologies which are move around the knowledge graphs are to node filling in and processing, and these activities could be organized in parallel. Knowledge graph allows us to postpone formal definition of scheme. We could start to develop application having not to construct relational databases. There are three types of graph scheme interpretation. The first one is semantic, validating, which allows us to check consistency and completeness with respect to template set of relation, and emergent, which considers the capability of the knowledge graph to evolve in time. In this slide, we present examples of the interpretation, and the first, in the figure 10, there is example of domain description as a scheme. The second one contains a set of relations. By means of these relations, we can check the consistency. In figure 11, there is ad hoc data representation, which later are to be upgraded. Another aspect of application development is the linked open data requirement. Web application developer should make a choice how complete application will obey to requirements, and these requirements are shown in this slide. Completely opened and interlinked application should have links to other resources from the published document according to Web3C standards using non-proprietary format. In this slide we listed vocabularies used in our applications. The first one is a friend of a friend, which is very convenient to express agents, that means organizations, persons, their activities, links between them. Vocabulary provenance was developed to express investigations, and it is useful to link documents. Doubling core, it might be the oldest and most useful vocabularies. It is used to describe published document, the author, title, validity, period. Wikipedia is very convenient to express personalities and instances. For example, in an application we used notion of passport. This notion we describe it as URI from Wikipedia. Open annotation. It was developed to express bookmark information, but it appears that it is very useful to express structure of documents. And the scheme vocabulary, which were developed by Google, Yandex, Yahoo, and other companies, contain different notions describing almost everything, but we use it as a last resort when we cannot express something in the previous ontology. Additional ontologies, non-standard ones, also can be developed. We need some information about existing ontologies. There is a so-called linked open vocabularies site which contains descriptions of most popular vocabularies and services for searching notions or keywords in ontologies, viewing ontologies as graphs, and loading them as RDF files. So let's consider some applications. The most complex one is to support informational infrastructure in Baikal microbiome research. This research is based on sequencing DNA and representing data as a cloud and processing stored data by means of various high performance algorithms, as well as publishing information as documents. The main problem is to involve biologists in the process of next generation sequencing data processing, and we propose to organize computational process as workflow diagrams, and the main problem was to represent current libraries as these diagram blocks. As a playing ground, we have chosen Mathur. Mathur is a complex software consisting of different operations on genetic data. In order to represent operations, it contains 144 operations, and we had to present these operations as workflow blocks. There was two ways to do this. One is to do it manually, but we do not like it. And the second one is to process mature source code and generate modules with some automatic procedure. And the top side we can see this part of source code describing an operation, its input parameters, output parameters, and parameters controlling the algorithms. At the left part we can see the generated code as a Java class representing a block, and to the right we can see the description of the translated source code as a knowledge graph represented in specially development vocabulary. We call it Mathur and NGSP. After 2 years of development, we observed that there appeared new project called Galaxy, and developers described Mathur's modules by means of Galaxy XML module description language. We also created a translator from this representation to knowledge graph and get some additional information, which is very useful to construct these Java modules. The transformation is implemented as model-driven architecture, which is shown in this slide. It contains a computationally independent model, which we consider the source code of Mathur, and platform-independent model. It's a template of module generation in Java interpreting this computational independent model with model of computation. And platform-specific model, it's a generated source code of modules, which is done automatically by means of analyzing platform-independent model in context of platform model. So we generate code of objects and additional data representing set of modules for RapidMiner for constructing this workflow. Within transformation, we use additional information from various sites. For example, DBpedia, WordNet. In general, we also can use UML representations. This is general representation of our applications. The application is constructed as a set of configured components. The kernel of the system is a Cleopatra knowledge graph server, which has Sparkle endpoint, a Penguin engine, which allows us to incorporate in web applications inference engine. Other components use kernel services. Model-driven architecture use Sparkle queries and Penguin to get model data in construction of its inference. As I said, transformations can use additional resources as DBpedia, and these resources are available via their Sparkle endpoints. This component provides capabilities to evolve knowledge graph and recognize additional structures, for example, for model transformation or document authoring. This component is used to construct documents which are stored in text indexing engine, as well as other documents has additional information. Some of these documents has no logical structure, for example, PDF documents or image scans. And these documents are processed in text document processing unit, which query text indexing engine for data, recognize text and its structure. The results are also stored in the text indexing engines. Required information converted to parts of knowledge graphs. This unit represents application itself. It should not necessarily be a web application, not necessarily be constructed as a complex of these units. For example, if we develop some JS application, it could be Quantum GIS, which has no notion about knowledge graphs, and we should construct additional data exchange interface, allowing us to use powerful routines of this JS system to process knowledge graph representation of spatial data. During application various operations of data stored in knowledge graph or in other databases, we also convert its metadata, which is shown here as this unit. The metadata conversion allows us to automatically describe results properties, and as we can suppose, any resulting data could be input data further processing. The transformations are implemented in logical languages like Prolog and its extension of Logtalk. In general, transformations are presented as a set of objects, passing their results between them and generating source codes of subsystems. This box represents terminological boxes which use it in platform model to convert abstract models into platform-specific models. This slide describes the properties of Logtalk language, which we use to represent the transformation. The main ones is it has very flexible semantics. It allows us to get rid of these blank nodes, convert, I could say, low-level representation of triplets into the high-level representation of object under transformations as more complex constructions. And the second property is that Logtalk can be used as a macro package. That means program is converted into final Prolog program, and if programmers do not use dynamical objects, Logtalk became just a form of knowledge expression and processing. Using regular languages for implementation of MDA transformation allows us to use already written libraries in this transformation. There are some special languages like ATL. Usage of foreign libraries is very problematic. In the following slides, I will show some technique of recognition and platform-specific model generation as Logtalk objects. At the left-hand side, we see knowledge-based representation of a class, and at the right-hand side, we can see an example of a query and recognition object which queries this graph by means of RDF predicates and express the resulting statement as a class, attribute and method with the necessary parameters. If we'd like to recognize class identified by ID and name, we should get the context model and try to get there something which has a type of UML class, and it should have a literal name. The same for attribute, but we supply class name at the first place. The platform-specific model is represented as tree of blocks. This idea was taken from library LLVM Lite, and it allows us to extend the program by means of adding, appending or prepending in these blocks. The final source code generation is traversing this block structure in depth. This is an example for constructing Python class. It is a specialization of the previous abstract class code block. Here we supply the method of source code generation and additional parts or special variants of part of this general scenario. Logtalk has the capabilities of constructing objects by means of inheritance of classes or inheritance of prototypes, as well as composition of objects using categories which are essentially prototypes but could be added to any object. Their purpose is to extend objects' behavior with the additional behavior represented as a set of logically connected methods. So using MDA principles in the first project allows us to automatically convert source code description into the set of rapid minor blocks, and it is easy to see that Prolog and Logtalk are very convenient instrument to do so, except some problematic points. For example, very simple tasks take too much efforts to do, for example converting an identifier into camel case. Another example of application is an authoring tool where documents are created by means of composition various parts generated by different algorithms, and some of these parts can be interactively edited by user refining the final document. The original idea was to represent document for study courses. In this slide we present general idea of document construction. Parts of documents are stored or generated on linked open data servers, and pattern-driven inference engine infer these documents, loading this part and replacing fields or structures by another structure. The document structure is described using open annotation ontology, which is originally developed to describe various resources. For example, it could be a bookmark of a web browser, and it contains two main parts. The first one is a point to target resource, for example web page, and another points to a description. This node describes resource as a text. This one points to the protein identifier. The third one is a semantic tag. Other are related to software used to get these descriptions. But we use this ontology in opposite direction. We describe structure of our document in this annotation, and then by means of web algorithms we convert it to the final HTML representation. In this slide, we can see an example of representing title page of a study course. These parts are generated from common template, replacing name of chair. Another source of final document representation is algorithms which parse study plan, take various information and construct part of document out of this information. In this slide, we can see the hours spent for various activities. This one is lections, personal work of student, laboratory works spent in a class. This is format of document representation. These exposed tags denote the places where we should take parts of document template, denoted by namespace and identifier. Replace this tag with title page content. Within this replacement, additional replacement could be applied. This is a template of document. General structure is fixed. The name of chair. These fields are also taken from study plan, and the additional information could be edited. We constructed a prototype of such system, expressed a pair of study documents, and showed that it could be useful, but it is very fragile, because if we have some marked up semantical information within the text part which could be editable, we could lose this information or break a format. So the further development is to construct semantically driven editors which could respect existing markup information and have tools to add new ones. The last example we consider is a cartographical web service where data is represented as knowledge graph. The problem is that most of nowadays JS systems, for example, quantum keys, represent data associated with objects as just one table. And if we have a very complex data, we result in very rare field tables. The aim of this JS is to represent faults of South Siberia, and for each fault we have additional information. For example, depth, list of earthquakes happened nearly, name of this fault, and the set of attributes known for a fault is varying from one fault to another, and it results in too many null values in this table. I gave this work to my student, and he constructed knowledge graph with the following form. It is flat, it has only one subject, fault ID, and all the relations is just non-null values for attributes. This vocabulary was uploaded to GraphDB source for personal use. He developed application using React.js and Leaflet.js. It took about 2 months. This application allows user to select 3 different aspects of data representation and filtering and construct an image. The further activity is to upgrade the structure of this knowledge graph, adding notions in sense of nouns. Not only faults, but also notion of value, earthquakes, quality, etc. And for this knowledge graph of faults, we also tried to extend the application with natural language access capabilities. There is so-called GeoBase program, which was developed in 1988 by Borland for their product Turbo Prolog. GeoBase shows how English language could be used to query geographic database for United States. You can get information about number of citizens of states through which Mississippi River runs. In order to connect our knowledge graph, we implemented 3 additional language forms: fault in continent, a fault with feature, or name of a fault. Feature of fault we implemented interpreting various relations taken from knowledge graph. We allow to represent these relations as a feature of fault when the feature is described exactly as a subclass of object property. For the fault, we need to just check that it is an instance of a class. We created simple web application where a query could be typed, but the results are shown as a list of answers. In conclusion, I would like to say that Web 3.0 technologies, which we consider including semantic web and knowledge graphs, are convenient and productive basis of application development, allowing us to integrate on various levels of software representation, from data transferring to abstract model transformations. We can utilize many various assets located in internet to utilize additional resource in our application, for example, DBpedia, WordNet, various metadata about existing vocabularies. To be brief, I would like to say that the main results of our development are related to new techniques for data processing and model transformation using Prolog-based logical inference. Now we investigate and evaluate various aspects of Logtalk language as an instrument for knowledge encapsulation and processing, as well as a complex data synthesizing engine. Thanks for your attention.